Hello, everybody. Welcome back. Today we're going to be looking at Unit 3.13, which is the final subunit within Unit 3, and its topic is on the Beer-Lambert Law. So let's get started. So what you're seeing in front of you is another example of spectroscopy, which we have talked about a couple of times now, where a sample of something is exposed to some kind of electromagnetic radiation and we get a readout from it, and that gives us some information about that substance. What we're going to be looking at today is specific. It would be using a device called either a spectrophotometer or a colorimeter, where you take a little plastic container, and that's what's in this picture here, called a cuvette. You would put some sort of solution into it and insert the cuvette into the colorimeter. The colorimeter then shines a beam of light of a particular wavelength through that cuvette. And there's a detector. If we're looking at this picture here, there would be a detector on the right-hand side that would measure how much light got through that sample. And the amount of light that gets through gives us information about how concentrated that solution is. And if you think about it, guys, the more concentrated the solution is, I mean, let's think of something like cherry flavored Kool-Aid. Okay, you take the powder, you dissolve it in water. If you are a person that likes your Kool-Aid very, very sweet, the color of your Kool-Aid is going to be like electric red. It's going to be very dark. Okay, if you were to shine a beam of light through your glass of Kool-Aid, very little light is going to get out the other side because there's more dissolved solute particles in the glass that are going to block that light. So your Kool-Aid would have a high absorbance. It's absorbed most of the light that you tried to shine through it. Whereas if you're a person that likes your Kool-Aid more dilute, you're not going to put as much of the mix in. Your Kool-Aid is not going to look as electric red in color. If you tried to shine a beam of light through that Kool-Aid, much more light will get through. Your Kool-Aid did not absorb as much, so it would have a low absorbance. So that detector measures how much light got through or didn't get through is really more what we're looking at. And this can be related using a chemical formula called the Beer-Lambert Law, and it is on your equation sheet. Sometimes people call it the ABC equation. So that capital A stands for absorbance, and absorbance does not have any units. Little a is something called molar absorptivity, which is a constant value based on whatever solution you're testing. That'll usually be given to you. B is the distance the light travels. Sometimes that's called the path length, which is measured in centimeters. That is typically the width of your cuvette. A standard cuvette that you would likely use in a lab would be a 1 centimeter cuvette. They're real small. And lowercase c there is concentration. And look at the units. Moles per liter, that's molarity. And again, little a and little b are typically going to be numbers given to you in the problem. Your unknown is likely to either be the absorbance or the concentration. And if you look at this graph here, they have a direct relationship. The greater the concentration of your solution, the more light will be absorbed by it. Okay, so if your solution is very, very concentrated, very little light is going to get through. The detector's not going to pick up much light, which means that most of the light was absorbed. High absorbance. So let's look at a sample problem here. And this is going to pull in topics, some review topics. So it says a 3.89 gram sample of an ore is completely dissolved in concentrated nitric acid. The mixture is diluted with water to a final volume of 25 milliliters. Assume that all the cobalt in the ore sample is converted to cobalt ion. The first question says, what is the, and then you see those brackets. Let's review, guys. Remember what brackets mean. Brackets mean molarity, concentration. What is the molar concentration in the solution if the absorbance of a sample of the solution is 0.45? Again, remember, absorbance does not have any units. So I want you to look at the graph, and based on the absorbance that's given, I want you to estimate a molar concentration. All right, so let's check your estimating skills. Okay, they told us that the absorbance was 0.45, so that's, right about there, and I follow it over on the graph, and that falls right about there, 0.08080 molar, okay? So sometimes you'll have questions that will ask you to simply, read off of a graph, okay? And then we're going to keep going with this to review. The next part says, calculate the number of moles in the 25 milliliter solution. Well, based on what I've just answered, I know my molarity, 0.080, and I do not know the number of moles, but I do know the total volume. Remember, guys, molarity needs to have its volume in units of liters. If you plug in milliliters, that's not going to work. So let's type that in and let's see what we get. And that's moles of the cobalt ion. Okay, and I was able to do that because I got the molarity off of the graph. Okay, calculate the mass percent of cobalt within that total mass of 0.389 grams. All right, well, then all I have to do here, guys, is convert the answer that I just found from moles into grams. I'm going to look on my periodic table. Molar mass of cobalt is 58.9. And let's convert that. Do that quick conversion. And at this point, it doesn't really matter if you're writing your answer as grams of cobalt or grams of cobalt ion. It really doesn't matter because remember what the question said, assume that all the cobalt in the ore is converted into the ion, so it's going to be the same amount, okay? So I now know how much cobalt I have in there. A mass percent, remember, is grams of one part divided by grams of the entire sample, and then multiply that whole thing times 100. And that gives me, I'll put it down here where we can see it, approximately 30.3%. Okay, so those second two bullets there in that question, bullet points, those were actually review. The only thing new here was that first bullet, looking at the graph there, okay? But I'm just showing you ways that they could bring in older topics, all right? Now, before we finish up, I want to just talk about a few other types of questions that might come up. When we're talking about spectral analysis, these colorimeter kind of questions, they often ask questions like an error was made, what could have caused this error? For example, if you look at this graph, I wonder if you notice that that one point is kind of off of where it should be. Please notice when we say it's off of where it should be, it's below the line. The absorbance is less than it should be. If I were guessing as to what made that mistake, because clearly the experimenter has made some kind of mistake, the experimenter thinks that they have put in some kind of a sample that was 0.050 molar. But since it is not, since it has a lower absorbance than it should be, my guess is the experimenter made some kind of mistake that caused that solution to actually be less concentrated than it really is, than he or she thinks it is. So maybe when the experimenter was putting the solution into the cuvette, there were some water droplets in the cuvette, okay? If you think about it, if you put a solution into something that already has water in it, it's gonna, those little water droplets, as small as they are going to dilute the sample just a little bit. So that would be a cause for that error, is that the solution was actually more dilute than the experimenter was expecting. What if you had a dot above the line? Okay, what might be a cause for that? Well, if you haven't done a colorimeter lab, one of the things that you're required to do before you test each sample is you take your cuvette and you take it's almost like a tissue, but it's a special kind of tissue that doesn't have any lint or anything on it. And you wipe the sides of the cuvette so that it's absolutely crystal clear. You want to make sure that there are no fingerprints on the side of the cuvette, because think about it, guys. If there is a fingerprint on the side of the cuvette where the light is trying to get through, that fingerprint is going to block some of the light. Not as much is going to get through. That's going to cause a higher absorbance than you're expecting, because that fingerprint absorbed some of that light. So if you were to ever see a graph that had a dot above the line and they said, what is a possible cause of that absorbance being too high? My guess would be this experimenter did not wipe down the sides of the cuvette and maybe there was a fingerprint there. All right. The last thing that I want to go over with you, and this is review from Chem 1, but when an experimenter creates a curve like this, they're making solutions of each of those concentrations. So the experimenter would start with, kind of work backwards, maybe have a solution that is 0.1 molar, then they dilute it a little bit, they make one that's 0.08, they dilute that one a little bit, they make one that's 0.06. So they're making different concentrations. Let's say that you have a standard solution that is 0.1 molar, okay? And your instructor says, I want you to make a solution, so we can make a graph, I want you to make a solution that is 0.02 molar. Hopefully you guys remember back from Chem 1 an equation that looks like this. M1 V1 equals M2 V2. it's called a dilution equation, okay? You have a standard solution that is 0.1 molar. All right, and your instructor says to you, I want you to make a solution that is 0.02 molar, it's more dilute, and I want you to make 10 milliliters of it. All right, you would use this equation, M1V1 equals M2V2. Think of one side of the equation as your standard solution and the other side as the more diluted solution. Think of it as almost like a before and after. Concentrated on one side, dilute on the other side. So if this were my task, I'm going to put the more concentrated solution on the left. There's its molarity. I don't know its volume. But on the right-hand side, that's the one I'm supposed to be making. That's the molarity I'm supposed to make, and that is the volume that I'm supposed to make. And if I solve that, I get this. Okay, so let me help you guys understand what that even means. That means I have this bottle of 0.1 molar standard solution. I would take out of that bottle just 2 milliliters of that concentrated solution. To get it up to a final volume of 10 milliliters, I would simply add 8 milliliters of water. 2 milliliters of the concentrated solution plus 8 milliliters of water is going to get me to that volume, 10 milliliters, that I was supposed to make. And when they mix, I will have the molarity that I was supposed to get, that my instructor told me to make. So I just wanted to review that M1V1 equals M2V2 with you, because sometimes questions relate to that with this spectral analysis business. So, ladies and gentlemen, that is the end of Unit 3. This was a long unit, lots of information here, but you've held on, you've done it, and I hope you've learned a little something, and I look forward to seeing you in our next unit.